Okay. You can self-introduce yourself. Many people who will watch the video.
That's not.
It's okay.
Okay, so hello everyone. My name is Yue Hu, and as Gennaro said earlier, I'm also professor at the University of Waterloo, but I'm in the department, so this is the electrical computer, and I'm in mechanical electronics. I specialize in robotics as well, but different type of robotics than Gennaro does. Mostly what I have dealt in my life have been leg robots. So robots with legs, meaning humanoid robots with 2 legs or other type of robots with more than 2 legs, let's say 4 or 6 or something like that. I have mostly worked with 2-leg robots. So today we're going to see some examples of applications in robotics more targeted towards leg locomotion. Leg locomotion is a very complex problem. Today I'm mostly showing videos for you to see what we can achieve. We're going to stay quite high level. I'm not going to do the mathematical details because they are quite complex and so we don't have enough time to do that. But as Gennaro said, I think it's good for you maybe to see what you can do with optimization techniques or with what is optimal control and what are the possible span of applications in robotics aside from maybe what Gennaro has showed you or what is going to show you after this part of the lecture. Okay, so let's start with. Okay. So we're going to see 3 main topics today. The first is actually not about robotics, strictly speaking, but I would use it as an introduction to the second part. So the first part is I'm going to very briefly talk about model-based optimization and model-based control. What very briefly, very high level it means, and then talking about human walking method. So how can we analyze human functions using optimization as well? I use that as an introduction to leg robots because they are very similar problems. Because humans also have 2 legs, we walk with 2 legs, and that's basically the same thing as humanoid robots. And the way we tackle the problem sometimes in both biomechanics and also in robotics is very similar. We basically kind of treat humans as a kind of a robot. So that's why the problem is very similar, and I could use that as a sort of an introduction to the second part that is on the motion synthesis and control of leg robots. And I'm going to show you a few works from myself, but also from colleagues from the field that are about leg locomotion on 2 legs and also 4 legs. And then last but not least, a couple of applications on interactive robotics. So what is interactive robotics? Are robots that interact either with other robots. So you have multiple robots with the same setup, or robots that interact with people. So you have a robot or multiple robots and a person. So this is another field of applications where we can also use optimization of robots. Okay, let me start from model-based optimization. I'm going to show you a formulation that you might, I'm waiting for it to appear on the other screen, that you might feel a little bit familiar with from the lectures you've had before, but you also might feel that this is a bit different. Disclaimer, everyone has their own notations, so do not worry, throughout the presentations you see a few different notations. This is in principle the notation that I typically use, and then when I'm switching over to other people's work, I just report their notation. So you will see different notations, but generally the meanings are similar. So you have your set of operating functions that you want to minimize in your optimization problem. In this context, since we're talking about more of the optimal control problem, you also have the control inputs that are here are represented by your inputs U. And then it is subject to a set of constraints. So some are equality constraints, some are inequality constraints. Depending on the problem, that part, the whole setup of this problem is what's actually going to define the application that your application will define these constraints and also your object functions. So roughly speaking, in model-based optimization, you also have an objective, and this objective could be of types that you have seen during lectures before. Could be, for example, I want my robot to reach a desired posture, I want to minimize energy, or something like that. What's the model part of the problem is represented in your constraints. So that part of constraints is basically the model of your robot. And that is basically what we actually mean with model-based optimization in a very high level, roughly speaking, manner. And that model can be a dynamic model. This is the one that we're going to see throughout today's lecture. And it could be of a robot or it could be of a human, as we're going to see for motion analysis. And that means that in solving your optimization problem, you want the dynamics to be respected. So you want your system to be dynamic. So now that we know roughly what model-based optimization means, let's see how we could apply that for human motion analysis. So the goal in human motion analysis is to analyze, if it works, is to analyze how humans move. So the video that you see here in the presentation was generated using Open Control. So the motions were kind of generated. I will show you exactly how this is done. And the motion that we're going to talk about, especially in this case, is going to be walking. And we downgrade a bit the problem from a 3-dimensional walking problem to a 2-dimensional walking problem so that we can look at the walking motion just from the side of the plane. So the kind of motion that you see here in the video. So we can disregard the latter. This is due to some background about the complexity of the problem, because 3D is way more complex than 2-dimensional. And even if this is 2-dimensional, this model has a lot of bits, right? A lot of joints. So its model is already pretty complex. If we expand this to a 3-dimensional space, then the model would be way more complex than what we have here. So how we actually tackle that problem, it's similar, as I said earlier, both for humans and bipedal robots. So both of them have 2 legs, right? And both of them have multiple links. So if we model the human as a kind of rigid body structure, this is pretty much the same way that we are seeing robots. What's actually changing is how we generate the controls in a way for our human, respect to how we generate for robots. Robots need to take specific control inputs for them, right? Each robot might be position control, in that case, we got positions. Some of them are torque controls, and then you can input torques. For the case of humans, we want to do this to have a dynamics analysis of the human. Because typically what we can do with human motion is that we can record the human motion, so how the human is moving, but only in a kinematic way and not in the dynamic way. So if we want to know, for example, how the torques are, what are the torques at joint level for humans, we don't have a sensor that can measure that torque, right? In robots, it's easy because you have a lot of sensors that allow you to do so. But in humans, not trivial. So we can use, in this case, optimization to achieve this type of, to obtain this type of information. So how it actually works is that normally we would record an actual human motion to analyze the human motion. So in this image, you see a typical motion capture system that is a marker-based system. So via these markers, we can have a reconstruction of the human motion from a kinematic perspective. That means that we know how each segment of the human body is moving in the space. And then we want to fit that kinematic information onto a dynamic model. So we do basically kind of inverse dynamics. on top of our model. And in the human model, using the human model, we add a bunch of constraints so that it is dynamically consistent, as I said earlier. So that means that the model, it has, if you just use kinematics, for example, your human could be also floating on the floor, and that is not matter. So that's not something that dynamically would make sense in the real life. If we want to respect physics, right? Our feet should be attached unless we're under different gravity conditions. But normally on Earth, our feet would be attached to the ground, and there will be certain ground direction forces for which the dynamics should be respected. So those constraints allow us to obtain dynamically feasible information by using optimal control and optimization. Walking, however, is what we call a multi-phase problem, in the sense that if you think about walking, let's take, for example, the level ground walk as an example, right? You have different phases. You have when your both feet are attached to the floor, and you have moments when at least one of your feet is not attached. And then you have moments when one of the foot is touching the ground, and the touching moment will create an impact. In a dynamic model, this would cause a kind of discontinuity, and we would have what we call a hybrid dynamic model. So you cannot describe a walking problem as a continuous problem per se. We have to take into account those different phases. So here you have a couple of examples of different walking situations for walking on flat ground and also climbing stairs. The walking phase is a bit different. It's also based on the terrain or the environment in which you're walking. You have some differences. And because we have those discontinuities, we need to consider those information. So those will be the contact, the fact that you have changes in the contacts between different parts of your, in this case, the different parts will be the two different feet with the ground, and the fact that there is an impact when you change these contacts. So you detach and then you retouch, and when you retouch, you have this impact happen. Right? So those information need to be taken into account when formulating your problem. I'm not going to into the details of these equations. So this would be just roughly speaking the way you can model those contacts and impact. So you have different set of equations for your contacts and for your impact that are going to be used for different phases of your optimization, which means that the optimal control problem that we have seen earlier has to be changed into something that is a multiple phase optimal problem. So the original problem that we have seen at the beginning, that was a one phase problem. It means that if your problem is all continuous, right? You can just have that as you can have a one shot and one solution for that. But since in walking we have different phases to respect, and there are some discontinuities that we have to take care of. We want to model that as a multiple phase control problem, where you have in your constraints your dynamics that describe your contact dynamics. So those would be the set of equations that describe the contact dynamics, as well as your impact dynamics. So that would be when you're switching from a contact to impact and so forth. And this multiple phase means it can be solved in different ways. I'm not going to go into the details of how this could be solved. But you will also need, of course, some constraints that allow you to transition from one phase to the next one. So there will be some continuity constraints between each of the phases, because we also don't want solutions that are completely detached from each other, right? You don't want this big discontinuity between each of the phase. But yet you do have to take care of those discontinuities because of the way we are modeling. So yeah, and here maybe a note on the fact that we have made some assumptions on this model for which the contacts and the impacts, the contacts are rigid and the impacts are instantaneous and elastic. Based on how you model your contacts and your impacts, the problem could also be inverse instead of hybrid, instead of having discontinuities, but that will be probably for another time, because that will have other issues in the modeling and solution of the problem. So the way the problem is formulated is that we have our states, which are basically represented by the joint velocities and accelerations, where the accelerations are computed using the forward dynamics. So we're kind of running a simulation of the motion itself. The controls would be just your the torques of the for your robot or for your human in this case. Because if you want to analyze the torques of the human, we want to compute those via the optimal control problem. The objective function could be anything. In this case, for example, we want to reproduce the original motion from the motion capture. So we want to reduce the error between the captured motion and the motion generated. I mean, between your state basically and the original motion capture. Because we want so that it's as close as possible, but because we have our constraints and make the model respect the dynamics, it will have some error. But the motion that you obtain is dynamic. And we have some regularization curve at the end that is minimizing the joint force. Then you may have some parameters. In this case, for example, you could, if you introduce some spring damper systems to simulate some effects of the muscles in your human model, which is often done for human work analysis. You may have those as your optimization parameters, and those are also normally outputs from your optimization as well. And some possible periodicity constraints is walking is often seen as a periodic motion, meaning that your initial state is periodic with respect to the final state, so that the final state, from the final state, you can loop back to the initial state and continue like this. So there is an assumption. Of course, this assumption does not hold when you start walking to when you are you take your next step, but we can make an assumption that this is true. For example, when you are already walking. So if you're walking a straight line, we can assume that your steps, unless you're changing step length at every next step, or you have some walking issues, for example, those affected by Parkinson's disease and things like that, you can assume that the walking pattern is pretty regular, and that we can make this assumption on periodicity as well. So with this set of problems, let's go back. So with this set of states, controls, and objective functions, and using the dynamic model that we have seen just earlier, you can then have these motions that were all obtained from originally captured human motions. So they were all. You should have put the video of the original kinematic motion, where you can see that the human feet are basically floating on the floor, and the step looks like that in the step, but they're definitely not respecting any dynamics. So this is generated using the model that I described, making the problem as a multiphase optimization problem. In this specific case, the controls that I used were the joint torques, and my objective in this specific setup was actually to understand if there is any elasticity in the joints of the human during the walking phases. and whether the stiffness of this elasticity is a constant or could vary time. And you can obtain then your controls that are basically, in this case, what you want to analyze of the human. So in this case, the purpose was to analyze whether those stiffness, let's say, those parameters have changed over time. And the results that we obtain are then the time variation of those parameters. So, and with these, we can make some conclusions on top of those motions that we couldn't have otherwise if we had only the kinematics of our human. So that was a quick overview on how you could use optimal control and optimization techniques to analyze human motions. In a similar way, okay, with a very similar setup, so we can apply the same concepts to the control, motion synthesis and control of black holes. Oh, that's exactly what I said. So leg robots, especially bipedal robots, so robots with 2 legs, are extremely similar to the human model that I described earlier. The human model that I described earlier, I could have also said that that is a robot, and the same thing would have applied. Because also in humanoid robots, we most of the time assume, well, not just assume, but in reality, they have basically flat feet, which is an assumption that we had also in the human motion analysis that I forgot to mention. Though the main difference is how we would treat those walking phases, because while in human walking, for example, we have this toe heel to toe rolling, right? When we walk, we roll our feet. That assumption was made in the human motion analysis, we made an assumption that it was just a flat, instead of rolling, was just a heel to toe motion. And so that we had that kind of impact. In the humanoid robots, we cannot do that, actually. Because if we were going to do that, the robot would very likely tip over and fall, because they do not have the capability of doing this rolling. The feet of robots of humanoid robots at least, are still most of the time completely flat, for which if we just do this edge to edge motion, when we're on that edge position, the stability of the robot is going to be very low, and we would unlikely be able to perform such field control. And so in this case, most of the time we would assume that both feet would just go flatly to the next one, to the next position, and so on. And this is a old video that I like to show to show where we are with humanoid robot walking. Though the video by now is kind of old, I can say it's about 8 years old. To me, it looks like yesterday, but it is actually 8 years old. But it kind of gives you the sense of where we stand with humanoid robots. The problem is pretty hard, and attention that here, most of these robots, if not all of them, are using optimization-based techniques to achieve walking. That means that they have kind of either the actual model of the robot or some simplification of it that we're going to see. And they are planning the motions of the robots by taking into account a bunch of constraints and things and alike. But it's very hard still for the robots to. This is the best one where the horror just jumping off. That robot is actually from my previous lab, and they're not proud of this being shown continuously around. And now we also actually, so this happened during the Double Robotics Challenge, which was one of the biggest robotics challenge for bipedal robots I think no one constrained them to be the bipedal for that challenge, but most of people went for the bipedal robot. And I would say that things have definitely improved from 2015, but they have not changed drastically. So we are not too far from that situation yet. We can do better, but we can't do much better yet. So because walking is a complex problem, and if we want to formulate an optimization problem using the actual model of the problem, for example, as we did for analysis, that normally would take a lot of effort and a lot of computational time. This is one of the major issues that we are facing still, I would say, with model-based optimization approaches to problems. There are some advantages and disadvantages of doing model-based optimization. The advantages is that we could take into account all the dynamics components or a subset or simplification of that. The disadvantage is that you need your model to be rather precise and you need to be able to model everything. So for example, in the video where the robots were falling over, if you didn't model things properly, for example, the location of your handle, the contact with the handle, where your next step should be, you didn't take into account the wind is blowing, I don't know, anything, right? Things that are very hard to model, it can be hard to achieve a good result. Regardless, it is still a very popular approach, especially in leg robots. And the other thing that we do most of the time is to simplify the dynamics of robots so that we can account for some things that change online. So in real time, that means, for example, the few things I mentioned, right? So you want to be able to take into account some of the effects that come on real time that you couldn't predict before, you couldn't model properly before. And then maybe you can somehow measure via your sensors, via other external sensors. And so typically there are few ways of simplifying those dynamics. One of the ways to use centroidal dynamics. Centroidal dynamics means that you're looking at the angular momentum basically of the body. The most popular, I think, is just to model the robot as an inverted pen. This sounds like an extreme simplification, but I assure you that a lot of those robots involved in the previous video were very likely using these simplifications. Because this is very simple. You can linearize a lot of things, as you may know. I don't know if you have ever mentioned, but linearization is like it's easy to handle. So while the other models, the more complex models you have, the more non-linear situations are encountered. Breaking down the workflow at a very high level, there I would say roughly two possible scenarios. The first one is that you perform your optimization offline. So you use the model as complex as you want. And then with that, you generate some references. And then those references are executed online, and online you do some kind of tracking or some kind of reactive controller to account for possible external perturbations. An example of this workflow would be to have an actual whole body trajectory optimization, meaning that you have all the dynamic model of the robot. You generate all the joint trajectories based on the actual dynamic model of the robot. And those are then tracked online using something as simple as a PID. Another approach that is a little bit more involved and I would say more popular nowadays is to have an online planner. So this online planner generates the sequences of your feet locations or your contact locations if you are not only walking but also dealing with other objects or environmental situations, and have an online reactive controller that accounts for the real-time situation. In this case, everything is run online, so your content planner is generally running at a lower rate, so that is running basically slower. It would generate your content sequences, and then you can use either simplified, and then you can decide which level of simplification you want to use. You generate the actual reference trajectories using those that simplified model, so that is also running online, but maybe at a slightly faster rate. And online, you have a whole body controller that is often often implemented using quadratic programming to actually execute the motion on the robot, for which then you have everything that feedback both to the whole body controller, but also to your content plan, so that your planning is also dependent at this point on what's really happening in your environment, and you don't have to pre-plan your content. And because pre-planning your content would work only for a very static situation, but if you want to use your robot to do tasks that are in real life for more complex and more dynamic situations, you would want to do something that is more reactive. I'm going to show you now some examples of those situations. So this is an example where the motion was computed offline and then executed on the robot with, I don't remember which controller exactly, but it's kind of just tracking of the original motion. So in this case, the model of the robot, we try to make it as precise as possible. There were many constraints that were put into this dynamic model. And in this case, the goal is to do an overstepping motion. The motion didn't have any actual reference, in the sense we didn't give it a reference for the motion. And we didn't give it, I don't know how to make it big. We didn't give it any reference for the motion to be actually executed. It was first automatically generated by the optimization based on the constraints and on the objective functions that were given to the robot. In this case, the target was to maximize the height of the stepping. So that was one of the parameters, for example, that was in the that we wanted to maximize with the optimization. And together with other stabilizing factors, for example, this robot had some elasticity in the ankle, and we had to, one of the objectives was to minimize that elasticity, the effect of that elasticity in the ankle. Because if you have elasticity in the ankle, the robot would end up behaving very wobbly, let's say, wobble on the spots. And normally it's hard for this type of problem to be solved at the first part. And you would need to give it some initial condition that is roughly similar to something that could be feasible. So it's possible that you run it for the first time and you use the outcome that might have converged to an actual solution or not as the initial solution of your, as the initial condition of your optimization problem. And here is also worth marking that because these are highly nonlinear problems, the final result that you obtain is of course not a global optimum. So it is always global. So it is an optimal solution. It's not the optimal. And we can use a similar approach, for example, to compute for push recovery, where this was done only in simulation. You can simulate the push force on the robot. That is one of your parameters as well, and use a similar approach as to one with human motion as well. In this case, you want to try what you want to do is that the robot's final position has to be stable. So the robot should not fall throughout your the recovery situation, and the final position has to stay. So those are all parameters and optimization objective functions that you want to use in terms of your problem formulation. So in this case, I forgot to say that the first set of problems until this one that I'm showing use the approach of first offline optimization and then online. So in this example, the offline part was also done already on a simplified model. In this specific case, the set of equations that you see there are the set of mass dynamics. That would be basically the dynamics as if you have only one body instead of the multiple things. And the objective, this kind of problem where the robot has multiple contacts, right? Where it has to go upstairs, so it has to actually walk, take the next step. In this case, the stairs were kind of modeled as well within the model within the set of equations. And you have different objective functions that, for example, want to keep the center of mass close to the support contacts. This maintains the balance of the robot. This tries to track a certain reference height to keep the robot upright, and some regularization term to keep the motion stable. And that would be the resulting motion. I don't really know why they show multiple trials. I think it just to show that it is repeatable and not that you execute it once and it fails every next time. So in this case, I'm pretty sure that in this case, the contacts were predefined. So there were a sequence of contacts were given to the optimization, and the problem was trying to track those contacts by using the dynamic of the robot and the objective functions that were given to the problem. And that's the final result for a robot. So you can see that even if we have a simplified dynamics, okay, the motion of the robot is eventually full whole body, because then we use those reference trajectories to generate the actual whole body. The main difference between using a simplified model and a whole body model is that in this case, you can see that the other side of the robot doesn't move. For example, the left arm of the robot does not. While in the back there, in this case, where the whole body model of the robot was used, everything of the robot is moving. And the robot has a very funky motion that is unlikely what he wants to do. I don't think we would move our arm that way. But it is this is a sign that the actual whole body dynamics is used, because otherwise those arms would not need to move in that way. And the fact that they were moving that way was a consequence of the consideration of the whole body dynamics, for which they were probably needed for some dynamic section. A bit of a more advanced way of formulating the problem was, but this is you may see this as a similar problem as the previous ones. It is an extremely challenging problem for a humanoid robot to climb vertical ladder. The motors of the robot have been burned several times in trying to achieve this motion. This is very dynamic thing, so the problem had to be carefully formulated to not break the problem process. It was eventually successful after having burned a few motors. So that's the situation in simulation, and you can see in this case the robot had to take many different contacts and avoid some environmental obstacles. All those things that you see here, the ladder, the platform, the robot itself, are modeled as their own dynamic. They are each modeled within the open. And this is very slow. So this was also a few years back. I'm not sure it can do it faster right now. And the video is already sped times 2. So in real life, it was much slower. This time. Yeah, so that's just the same execution of the situation you saw in simulation on the real problem. So this is the other thing that is worth mentioning, that normally we would try things first in simulation and then try them on. And if you have a good simulator, the same situation should happen in reality, but it's very hard to have all the factors taken into account in your simulation. I don't know how to switch to the next slide. So in this case, the problem was solved in a kind of mixed fashion as the one I showed earlier. There is a offline multi-contact planner that takes into account the dynamics and the context of the robot. So you give a few parameters to this to the planner that will generate the contact sequences for you. And these contact sequences should be dynamically speaking, which means that then once you have those contact sequences online, you can use QP controller to generate the actual motion and to track to react to the real situation, but still based trying to stick to the real contact sequences. And then this QP controller, the quadratic programming controller, will send the controller, the actual control out to the robot and react based on the feedback from the sensors. As I said, in this contact planner, everything is modeled as its own. So you have the robot that is named HB2, the robot itself, the ladder, and other environment models like the platform and everything. They are all considered into your automated models. And then it would generate a sequence of contacts based on the dynamics of the actual robot. And the constraints include all the feasibility constraints as well, like the joint limits. So the robot for sure cannot exceed certain joint limits. So those have to be respected. Torque limits, reaction forces that are feasible within certain ranges, some friction probably, and so on. And then on the online controller, which is the multi-object QP controller, you have a sequence of tasks that are considered inside of your problem. So these tasks are mostly for tracking and for achieving certain desired postures. So in this case, we have the posture task, which is to track the desired posture of the robot, and as well as the center of mass, which is mostly to keep the stability of the robot so that the robot does not fall, tip over. Yeah, I'm not going into the math details here. That's just to show you how the optimization problem is formulated here. Okay, so it is really a matter of formulating your problem properly and being able to model everything. So if you know how to write your constraints, your objective function based on the model and the condition and the task that you want to achieve, then you can use optimization and to achieve. Using the same framework, you can also do something like aircraft manufacturing. I never really understood why would you want to use humanoids for aircraft manufacturing. In this case, there were additional information coming in, for example, from the cameras. So here we're also embedding the vision from the robots as well, where those inputs are also basically part of your sensor feedback, right? The camera, the force of sensors, the joint position sensor, joint torque sensor, are all that set of sensors. You do not necessarily have to restrict yourself to sensors that are strictly, let's say, traditionally giving you the information about the robot itself, but you can also use sensors that give you information about the environment. In this case, for example, where the object is, what the object is, where the robot should go. And the robot, because it's pretty slow, is gonna fast forward. We have to plan those contacts to be able to achieve these tasks. In this case, that it has to hold on that handle because otherwise it would. So it's kind of leveraging on the pole, okay, on the contact with the pole to keep the stability of the robot. Because otherwise, if you lean forward, even humans, if we lean forward continuously, we would fall eventually. So the same is for the robot. Do not mention that human and robots potentially have more weight on the upper hand. So if they lean a bit, they tend to. So similar approaches can be used for quadrupedal robots as well. In the quadruped model case, so in this specific case, everything was done online, so including the contact plan. So the contacts were also automatically generated based on your environmental model, the model of the robot, and desired outcome. And the main difference between quadrupedal and bipedal is that quadrupedal robots gait is a bit different. They are more similar to quadrupedal animal in a sense. And they are a bit more stable because they have 4 feet instead of 2. So your support area is way larger than two legs. And the gait on quadruped robots are also usually much faster because of the same reason, like I said. So in this case, everything was generated online. And they can make it walk on 2 feet. I remember this one actually. Go to the next one. So in this case, everything was automatically generated. So this is what we call gait synthesis. We're generating both the contacts, the location of the contact, how to switch from one contact to the other one, when to do these switches. So that's what the original offline contact planner will give you. The difference that in this case it is generated online, and then the execution is done via this sequential linear quadratic problem that basically optimizes the linear time varying feedback and the feed-forward controller for the quadruped robots. And then another example of quadruped robots being extremely agile. So I think this one is running what we call a model predictive control online. And it is pretty fast in the sense that these problems can be solved online relatively fast. Typically with a more simplified dynamics, but you can achieve pretty impressive. But I would say also because this is a good problem in terms of hardware. Okay. Okay, so that was about walking robots in general, and I will quickly go through the last part, which is about interaction. So similarly, you can also formulate optimization problems for robot arms, of course. And in this case, you have 2 robot arms, okay, that are kind of interacting with each other to perform some more industrial-oriented tasks. They are, in this specific case, what the authors are trying to minimize are the impact velocity. So you don't want the robot to have high impact on the object that they are holding, because that would probably destroy the blocks. And so you want to minimize those impacts while executing the motion on the robot. So this is also done online. And you can see they also have these patches at the end of the robot to try to soften the impact, but at the same time they try to minimize the impact velocity to have a feasible motion on the robot that is also not that big. You can also use optimal control for human-robot interaction. So in this case, you can see that in the set of constraints, you would have constraints that describe a bunch of environmental situations, including the human self. So we try to model also the robot in our the human in our constraints to avoid collisions or to avoid other things that may happen with the robot, so to keep the interaction safe. But at the same time, task oriented. So the robot is supposed to physically have a person, so that is the task of the robot, and it is dynamically feasible and safe at the same time because you can put all those information in your constraint. Last, this is an application that I have implemented a couple years back, where in this case, the robot has a couple of tasks. So it is also using optimization to perform those tasks to interact physically directly with the person. So the person is physically holding on the robot, but the robot has its own task that is generated using optimal control, using optimization. It's basically trying, the task of the robot is trying to catch higher value points. So the person wants, it's a point catching game. So the person is using kind of the arm of the robot to try to catch points. And the robot has a kind of, has its own task of catching the higher value. So whenever there's a higher value point, the robot's task is changed to try to catch those higher value points. This is a very simple formulation. Actually, it's basically just trying to minimize the error between where it is now and where the higher value points is, and then try to force its way over that location, bringing or not the person according to how strong is the person. Okay, so that's everything that I wanted to talk about. So I showed you a few applications, mainly for leg robots, but also for interaction. These are a bit more complex robotic systems that can be where model-based optimization and optimal control framework are commonly used to generate motions or to control the robot directly. Because optimization-based methods allow to exploit more the complexity of these robots. And while now there's more and more learning-based methods, especially for maybe more simple type of robot, for example, robot arms, these type of methods are still very hard to apply on, for example, human-like robots because it's just very hard to, for example, to repeat motions and try to learn from the errors. Because the moment the human and robot makes an error, it's probably already too late and it has already gone. So that's the things. One of the reasons for which we are still using model-based optimization techniques to target those problems. The formulation of the problem is probably the most critical part of this type of approach. If you're able to model everything, you will have a very good solution that is very robust and stable. But oftentimes it's very hard to be able to model everything. So this is one of the major constraints, major drawbacks of this type of approach. And again, the solution in these cases are typically local optima and not. So that's everything. Thank you for listening, and if you have any questions, so I think I'm running over time.
No, we can take time for questions. Thank you. if you have any questions now, you can ask them now. Also from you. I think there is already a hand raised there. But we can keep thinking, right? And you can ask them also again. Let's see, Pedro, I think, and then raised.
Sorry, did you say something?
Yes, I thought you had an hand raised, right? In Zoom.
You thought I had what? I couldn't hear, sorry.
It's not simple, right? Next to
Yeah, did you have a question?
you have a question?
Oh, no, sorry, I just used the clap reaction.
Oh, okay. Oh, that was the clap. Yeah, okay.
Yeah.
Yeah, go ahead.
I'd like to know what are the biggest difficulties in the area today, like is it processing, the methods we know, the materials? What's the biggest problem?
So the biggest problem you mean in like the type of application I presented? Or
Yeah, maybe for humanity. What
humanity.
is wrong with
The
humanity?
bigger question. The biggest question. So there are few problems. One problem is I would say is computational power at the moment. So is optimization techniques are, I would say, old by now. I mean they're nothing new, right? Like it's not like we discovered them the past decade. For sure, we have done a lot of improvements in the past decades. And a lot of technological innovation drove those new innovations, because before, even if we could imagine, let's say, and we could write those optimization problems, we wouldn't be able to achieve the result that we have today. So for extremely complex dynamics, it is still very hard to obtain feasible solution within reasonable time. Reasonable time meaning real time. So say that in the real time, in the robot, you want to have your control loop to run at high frequency, because otherwise your robot might fall or anything like that. So you want to be able to achieve real time control so that robots are stable. Which means that you need to be able to solve your optimization problems fastly. And that's, if your system is extremely complex, is very hard. So that's also why in the approach I showed, there are several layers in which you have layers where where your loop is run at a lower rate to allow for that computation time. So maybe, who knows, one day if we have better computation, though we're kind of reaching a limit of the computation power now. Who knows, maybe quantum will come and help us. Maybe things will change again. So I think that optimization methods are heavily, maybe not heavy, but they definitely depend on the power that we have, computational resources that we have. Of course, there's also a lot of other backgrounds, like how to improve those solvers that we're using for the optimization problem. And there's a lot of people working on improving those solvers, new type of solver, parallelizing these computation systems. So that is definitely the other thing, is that it is very hard to counteract for all the uncertainties. There are a lot of uncertainties that are very difficult for us to understand. Take, for example, a human-robot interaction. You have a human, and the human can do whatever, and how do you understand what is what is the person doing? What is the robot supposed to do? Right? That is very hard to tackle as a problem. If you have two robot systems, it's way easier, because you are probably in control of the situation of the robots, and you still have to deal with the environmental situations, changes, and so on and so forth. Yeah, if you have, and the reason for example, robots have been used in industry for decades, 60s, they work fine by themselves in a repetitive and static situation. But if you want to put a robot in an extremely dynamic environment, say you want a robot to go around and serve coffee to people around, navigating the space is a problem. what should the robot do if there is a person? Should the robot go around? What if the person tries to go around the robot? And so many decision variables there that you don't know necessarily how to model in a way, like how to mathematically describe them. Because at the end of the day, we need some way to describe those situations for the robot that needs to compute its somehow. A lot of problems still ahead, so be solved.
Maybe to comment on this is that if you like biological inspired robotics, we as a human, we are actually solving a model based on we have a simulator in our brain, the frontal cortex, that has a model of how it moves, built on the experience that we had from like we are very young. And we use that model to figure out how. So the approach seems in a way natural, literally with a big N, capital N. So that's the other thing is that we have a lot of computational power, much more computational power that is available on board of today's scopes. Right? The brain is extremely powerful and energy efficient. Yeah. We can build like thousands of CPUs and get the same power of computational power of a human brain. But that's gonna not fit on the robot and it's a lot of energy. Regarding the human robot interaction, right? Having model, if you want to use model, which seems to be the right thing, you need to have not only kinematics and dynamic model, right, of like how we move, but also cognitive model, how the human is going to intentionally how the human is going to behave. And if mathematical models of kinematics and dynamics were already somehow started to be developed more than 2,000 years ago, wrongly by Aristotle, that thought that forces were motion velocities, but still, he tried. There are no mathematical models of like motions or intentions. Like we are starting now, right? To have to try to cast these things, these higher level concepts. Once you have the math, then it's a problem of computation. Right?
Yeah, we want everything expressible in math.
Exactly, but not as formulation. More questions?
Okay, you don't have questions right now. I will be around to do that. So,
Yep.
if you want to talk about that.
All right, thank you so much. All right, so I think we can start. That's then the numbers. Before I turn it on again in a few minutes, because I just want you to recap, right, the main takeaways of this course and what you should have learned or what you should remember, right, when you leave this room. So takeaways. Let's see. Lecture 1, we started saying as also you learn, right, somehow this first part of this lecture that models are important to design controllers. And in particular, a specific type of models, which are those known as feedback. In the most general way, we have, or most general settings, we have a control block, which acts on a system block based on some information that comes from the system. Right? So that's the feedback branch. And these are the controlling groups, which have been, let's say, the objective, whose design has been the objective of these lectures. And in particular, we have used optimization techniques to figure out what this control block should output. And in particular, we have used a specific formulation, right, of these optimization techniques. So we saw in US presentation, right, that tasks can be somehow appearing in an optimization program in multiple places, right? We said, let's take as our main objective the minimization of the energy, So the robot should do its task in the laziest possible way. So that the tasks showed up as constraints in this application. That is something that is here. Somehow in here there is something. Somewhere in the system there was a differential equation, right, that modeled this system, which we called x dot is equal to f0 of x plus f1 of x times u, where x is the state and u is the control input. This case here u gives us an x, based on which the controller figures out what's the best u. And you recall this may be representing a bunch of things. Actually, this controller fine form is also capable of representing humanoids, quadrupeds, and all kind of mechanical systems. Everything that comes from analytical mechanics is actually in this form, with appropriate choices, states, and inputs. So this can be manipulators or white robots, which we said specified as xe dot equal to j of q dot or dot is g of q times u triple for manipulators and white robots. And they all have this form. The dynamic models, right, of these kind of platforms also have a term here, 0x, which is the drift and is probably the thing that creates most problems, right? You deal with the optimization in particular with visibility. Then we said, okay, let's figure out how to make this system execute the tasks that we want. And we said they're kind of categorized tasks in two categories. First one is what we call stability like, where we want the state X of our system move towards a desired set in the state space. This is the state space, which we said N for purposes. And we have a set S, towards which we want our system state to travel. And we had invariance of tasks, which dually consists in keeping the state as X of our system within a desired set S. This is the trajectory X of T. This is the trajectory, which in principle are trivial. I would say, sure, we need to approach this set. We will remain within this set. But the problem is in taking a control input U such a way that the state goes towards the set or remains within the set. That's not usually an easy problem. So we simplify from our multi-dimensional problem to a single dimension problem, defining the A control variable function CLF for executing stability like tasks, which basically consists in letting this function or A an appropriately defined function B of X of T move from its initial value at time 0 towards 0. And when this function moves to 0, we made sure that the state X. So along this line, we have x at t1, x at t2, x at t3. Correspondingly, we have v of x at t1, v of x at t2, v of x at t3. Right? So remember this picture. This is what we want. This is what we are capable of doing. Right? But since they are the same thing, we are capable of doing it. Dually, right? To keep the n-dimensional state x in the set S by choosing an m-dimensional vector to give, we can ensure that a function h remains above 0. So remains positive for all time. Starting from a positive value, h of x at t0, corresponding to x at t0. We have that as x evolves in this set at t1, t2, t3, our h evolves on the real line anyway, and remains positive. This is what? Because two properties, right? This CLF and CPF from very fun, which are a CLF is useful because as p goes to 0, so yes, p of x is equal to 0 if and only if x is 0, or in this case in the set S. So this is specifically when we want to drive towards the point. In this case, the CDF H is greater than or equal to 0 if and only if x is in the set. Okay. So keeping x in S means keep H positive. Going towards a desired set, in this case the point 0, means driving P. And how do we do that? Now we need the. Then I want to use this. Okay, this should be internalized right by now. Whole field, right? And all systems are have a control in the input. And whatever you try to model, this is the target modelation, right? Because it's computational. It's computationally in advantageous, right? So we were saying we would like to execute those tasks. So drive V to 0, keep H positive, and we want to do that in the laziest possible way by minimizing the energy spent proportional to the norm, square norm of the continuity. Subject to 2 times of those things. So there is what we call LF0 dx plus LF1 dx times u less than minus alpha 1 dx, which is code for p dot has to be less than or equal to minus alpha 1 d. Code for p equal to 0. The below an exponential that goes to 0. And that ensures that v goes to 0. To ensure that h is kept above 0, then we can enforce an analogous constraint where everything is the same, but the sign of this inequality is split. And these ensure that h dot is greater than or equal to minus alpha 2 of h, which means then h should be above an exponential that is always positive. So h should be here b goes to 0, h is. Now the nice thing is that given that control affine structure of the dynamics of x, we have affine constraints in the control input of this optimization. So this even also our lazy choice cost is a convex. Quadratic problem. And when you have complex quadratic problem, almost no matter how big they are, like how what dimensions does your position variable has, this can be solved very fast, very efficiently, and you can get to the global law. If you're able to express your objectives, control objectives this way, then you can get the best, the globally best of the best, to achieve your objectives. Last thing that we mentioned yesterday is that there is not all good, right, with optimization, because there is a problem. Not all optimization problems have a solution. There might be cases where there is no U that satisfies all the constraints. That's known as infeasibility. And yesterday we showed a way of dealing with infeasibility when we have one stability-like and one invariance-like constraint, which means in relaxing the stability constraint. Yeah? So we're saying, okay, we trade off the execution of the task consistently driving b to 0 or x to desired set in favor of the task of keeping x in the desired set, which is kind of related to safety. So that means keeping h positive as a higher priority. Now extending this, say we have n tasks. So first of all, let me write down this what we had yesterday. 2 L 0 x 1 x. And L 0 h x plus 1 x. So let's relax this stay here by introducing a so-called slack. Right? This slack is basically saying, you want to go to 0, u v of x, you want to go to 0, and you're going to go to 0 probably eventually, but not at the rate that you prescribe by these are common. So we are kind of relaxing, okay, you want to go down, the example of the hiking, you want to go down the mountain by running at 2 meters per second. Maybe not. Maybe you can run just a 1 meter per second. Or eventually, maybe you need to stop because of safety reasons. But this delta is the slack variable that becomes part of the optimization. Right? And it shows up as an optimization line. In the cost, because we would like to, if possible, relax this constraint as little as possible. We minimize the square delta. And this k is or kappa here, it's just a scalar value, which we saw in yes. Do you see that? No, you can experiment actually with that on the Google Colab, right? Changing that value. Right? How does how the behavior changes in response to the thing. We just said intuitively, if you have an enormous weight of delta squared, maybe it's worthwhile not moving echo, just relaxing this constraint to the point that you would need in the optimum. Yes, that's what we were yesterday. That's also a convex QP, by the way. This time in U delta. Right? So this gives us an output, the optimal U and the optimal delta, this one delta star. And what we do is we take this U star, we give it to the robot, right? In a feedback component. To stress again, once again, right, this feedback on this. We have the state, right, of our robot showing up here as X. Feedback control look like that. QP that gives us output Q star. And by the way, also delta star, but we don't care as far as controlling robot is concerned. We have our robot that gives us output state, which we take in the QP, plug it in here, and solve it. We get the U. Any questions about the last 5 lectures?
Is this the last lecture? Is this the last lecture? Oh, it was fast.
I'm glad, yes, it was not boring. Yeah, that's the 6th. Yeah. If not, let me show you a couple of things you can do with this kind of formulation. All right, so I think that so that's fine. Okay, so that's what what I briefly showed you yesterday. The application of these two manipulators, which is kind of an extended version to what we saw in the collab, right? For a simple, not that simple R. It's 3 joint, it's just as 4 joint, but it's in 3D. But the whole formulation is the same. It's just that the Jacobian changes or other dimensions change, but the formulation is all the same. And we said there are multiple tasks that we want to execute. There is a vision task, which means with the camera there is multi here, whose view is shown here. We want to somehow look at these dice, which is a point of interest in the environment. Then we want to move at some point the end effector of this manipulator to a specific location, while also looking at this point. And then we want to let do all these by avoiding the joint limits, right? Which are somehow the maximum and minimum value of each of the joints that the physical probability. These are multiple scenarios in which you can somehow get this execute this success. The setup is the following. Right? So the tasks are three. We have regulate and affect the pose, orient the camera to desired point of interest, and avoid the joint angles. So what kind of task is this? If we have to categorize this as stability or invariance, what is this? Okay. What about this? So, yeah. What about the avoid joint angles? Yes. I want to stay within the max away values for the joint angle. These are stability invariant. The way we formulate this is as follows. Now, in general, so the jet is always minimizing. We don't want to trace it in design if we don't need to do it. Each of those constraints, right, is represented by this function C task, right, which depends on X and Q, R condition, right? And it can be this, if it is a stability task, or like that, if it is a invariance. When you have multiple of them, and you don't know whether you can execute them all at the same time, invisibility becomes an issue, even with two tasks, an issue, right? So CLF and CPF assure us that there's a solution when only that is enforced. There's always a solution, but when multiple of them. So we can do, let's relax them all. Let's put slab variables everywhere. So right, but yeah, that does not look like that. Yeah, on Zoom is much easier. But basically, there's a delta for each of these tasks, right? And here we have the square. We are minimizing the square norm of the vector. So we're seeing, yeah, I mean, try to do that, minimize your square less than or equal to 0. But if you really can't, then you can increase the slab. You can slack it. The thing is, this might lead to not doing anything, and not moving. I mean, if your weight again on delta is too much, then you're not going to do anything. That's a problem. The advantage, though, is that since we have control on how each of these tasks independently is slack, we can enforce priorities for every single task. We can say, we are on the mountain. We don't want to right on the where were we? How there's more than 200 meters. We don't want to go down 200 meters. And there are 2 points. There is a ice cream shop. There is, right? And there is a water, right? Shop. And we want to get water and ice cream. Those are the 2 stability lines. We don't want to go down more than 200 meters. That's the invariance line. We can say, oh, but I want more the water than the ice cream at least. So let me prioritize going to the water instead of going to the ice cream. So that's what you can do with this. And so by staying about 200 meters, you can get perhaps if that's feasible. But you are going to get water if possible and not. That's the idea. Think what does that A times delta less than or equal to 0 mean in terms of prioritizing? We can express constraints like that, the delta 1 less than equal to delta 2 in this form, A delta less than equal to 0. And as a result, we are going to have the task 1, let's say the task 1 has higher priority than task. So that's the result of the behavior. Notice that this is a linear constraint delta, so no problem. This is still a QP. We still solve it fast and efficiently. And this is what was implemented on this robot. So as I showed you yesterday,
Have a delta, it's less than or equal to 0. It's the delta is a vector in case of
yes,
O. It's 0 on the right, and it's
might be a vector. Exactly.
okay.
Depends on the line on the road. If you're saying delta 1, less than delta 2, then your A can be just this. That's okay. If you have multiple constraints on the class, so you can delta 1 less than delta 2, additionally delta 2 less than B. Then you have 1 minus 1, 1 times delta 1 delta 2. Okay? You can do this sort. In fact, that's exactly the dimension of the K in this example. Because you have 3 tasks. So we can enforce relative priorities between them. And in this following this stack of tasks. So this is prioritized stack. Join limit avoidance, that's highest priority. We have visual synchroning, like driving, orienting and towards the that's second priority. At this point, there is no other task. So it is more important. The robot moves towards the camera towards the back. This shows the controlling and the velocity in this case. Now we insert here the position control. So we want to move the end effector towards the specific position. And this is done at this priority level. Then if we switch the priority, and so we have that K matrix to G. We can have end effector position be actually better than this. This also handles the case where the tasks can be executed all at the same time in the same way. If the water is at the same place as the ice cream, then you can get them both by executing any of them. Right? Because no matter what the priority is, right, you're always going to get both if they're in the same place. Right? That's similar to this case. We can be at the point and orient the end effector towards specific. So there is the reference in the presentation, so you can have a look at what this really looks like and the link to the code. Same for mobile robot. So we saw what happens with one robot. Let's see what happens with the 6. Right? So we have a coordination between the robots in this case, which basically have to arrange themselves on this rectangular area in an homogeneous way. They distribute themselves kind of homogeneously. Before it was a simulation, these are actual robots. So it doesn't look like these are real robots. These things are projecting down on the area where they move using an overhead projector. And this is called the robot area, which is also remotely accessible. So you can actually write code and upload it on this robots, which I used to work on during PhD. And you can do multiple things like assemble a shape, like in this case, all sorts of coordinated behavior. Right? But as you were saying, as also you were saying, one of the most difficult things in optimization is dealing with some uncertainties. And you don't have a model for these uncertainties. That could be a problem. So this kind of formulation using like a minimum energy, using constraints, is actually useful to deal with this kind of unpredictable behavior. Because your only objective is to minimize energy. Right? So if that obviously works in some applications, it's not something that works in any application. Right? But in application like long duration autonomy, when you want your robots to stay out for very long times, right? And you don't know what's going to happen, then minimizing energy is probably the best thing you can do. Right? Because you don't know what's best overall. Let's minimize energy and have different tasks as we say. Now, same task as we saw before, they should arrange themselves homogeneously. And then they should avoid these two obstacles, which are moving in the environment just to disturb them. So moving towards the homogeneous configuration is one stability like task. Avoiding this, of course, is an invariance like task. And then there are also these charging stations in the environment, which are used to recharge the battery when they're depleted of these components. So keeping energy above a minimum threshold is an additional invariance, as we talked about yesterday, right? With the invariance.
Something that's really interesting that we always mind how to show the chain information. Because you were employed. Because the other one who needs to know where the position of all the orbits are. One of it is all the two. To actually drawing ones.
Oh, you mean this projecting thing?
Yeah.
Yeah, projecting thing is just to highlight that the robots don't.
Okay.
That's a good point. That is a good point. How do the robots assemble this kind of homogeneous formation? They're actually, each of the robots is actually in charge, right, of just this region around itself. So each robot is in one of these regions, as you can see, which, by the way, are the Voronoi cells. So the set of points which are closest to this robot than any other. And to compute this Voronoi cells, you just need to see who is your input. You don't need to know anything. Like this guy, here, this robot, doesn't need to know the position of this robot to compute this Voronoi cell. Right? This is an issue or a property which is sought specifically when you deal with multi-robot systems. You don't want each of them to know everything of all the other robots. Otherwise, it might work with 2 robots or work with 6 robots. It might not work with 1 million, because then each of them needs to be able to compute something that scales with the number of robots. That's something undesirable. You want the computation to remain constant as the agents, the multi-agent system goes up. That's a good one. You can look at the implementation of this as well and see how that works. But then this is the behavior. So each of the robot tracks this point, which is the centroid of its Voronoi cell. And as a result, it's going to achieve this kind of homogeneous. This homogeneous kind of arrangement. At some point, either avoiding obstacle, and at some point, one of those is running towards this charging station as the energy slows down. That's the invariance, the energy. And as I was saying, like as they are moving and they're doing this kind of complex behavior, they're also avoiding obstacles. This complex behavior, by the way, is the laziest possible thing they can do. They are minimizing the velocity in this case. These are unicycle components. Like they're modeled as what we saw in the collab, right? With a longitudinal and angular velocity. They're kind of minimizing depth.
It's really fun. There's so much chaotic. It's really fun, but it's rather chaotic.
And of course, this is chaotic mainly because the energy are discharging very fast. Right? We have one example with the 4 robots, like with a smaller environment, in which they don't need to move that much. So they have to speed it up 64 times to see. And finally, the energy going down and one of the robots go to a charging station. This one was simulated to see the behavior, like multiple recharging cycles, but that's why it looks so. And most of the time, they should be standing still. Right? Maybe avoiding obstacles if they're moving too much. Yeah, so the tasks were these, I distribute homogeneously over the environment, avoid the obstacles, and avoid discharging patterns. Which, as we said, are stability like variance. This is this is a good link right on the code of GitHub. Notice how the resource is called multi-robot task allocation. So it's not just that you are executing these tasks in a prioritized way, but you can also allocate different tasks with robots. So this repository contains the code of this, but also when you have multiple tasks and multiple robots capable of doing different tasks, you can allocate tasks and output using this simple nature. There's only one more constraint. There is the one on the other. You want, I don't know, you are a group, you want to get ice cream and water, right? And again, okay, I need to carry water and ice cream for 10 people. I need at least 2 people, right? Otherwise, I cannot carry all the ice creams and all the water for everyone. So that task requires 2 people that are capable of carrying things, right? Like, so this kind of constraints are the additional ones to this distribution. Okay. Yeah. So one last example. You said that there was how do you say it? Complex, but chaotic, because you didn't see this. So in this case, which is this study of resilience, as is known, which again deals with the unknowns in the environment as well as in the robots. When you have multi-robot systems, the code for this is also the same. So it's like the kind of the flavors right of this. And let's look at the final. Yeah. Experiment with the unit. So here we have this topic. So here we have 5 robots. One of them is has this kind of helicopter projected on it. It just means that it can fly over this area and it can move over this area. We're just simulating one of the robots to be able to go across this area, which is kind of representing an area where these ground robots are not able to move, like a mud or a basin of ice, yeah, exactly, water. I think that they cannot move. Whereas this one is capable of moving. And the tasks are the following. One of the robots, we're not saying which one, has to track this red circle. When it is going to move in the environment which is red cross. 3 more robots have to escort it by arranging themselves in a circular formation when it moves towards this red cross. And it's, oh yeah, there was one last thing. They have also some kind of sensors which has to point to this stuff. So that would be a camera, for instance, to look for some point of interest or some kind of, if they need to protect it, maybe like some adversary or whatever. But these are the goals. These are the tasks. These bars that are plotted, are projected next to each of the robots, denote the capability of the robots to execute the tasks. So red is for this kind of arranging in around this circle, and blue is the one to look at this stuff. So these are the capabilities that the robots have. And when the optimization starts, we're gonna see that here we go, like robot number 4 is assigned to task that needs to go along this trajectory towards the red cross. Robots 1, 2, and 3 are assigned to look at this point while protecting the other robot. At some point they switch because the sensor of this robot 3 broke. There was the red flashing. There was the red flashing cone here. Okay. okay, that broke at some point. This is not able to execute the task anymore. So we switch by using an allocation to switch. And then as they proceed, I think we have some speeding up of this. So you see, this is the trajectory that the robot here should track. Yeah, so in this region, this robot is getting stuck. It's not able to process. So as it gets stuck, its capability of executing this task goes to 0. So it cannot be considered anymore. He's lost there. And this robot that is able to do it is recruited and assigned their task. And is joined 1 and 2 to a spot at B. Again, they were doing the laziest possible thing, minimizing their energy, subject to this constraint of executing tasks. Which robot should execute, or how many robots should execute each of the tasks, and with which priority, which results in again, the code, I think, rather kind of accurate, not accurately, but densely connected with something else. It might be possible to understand this, but also from the reference, actually, you might be able to. So that was the last thing that I wanted to show you. I think one last reminder is that from to the day of Monday, there's going to be this conference organized by the FGV, where you and myself also going to give talks about optimization in different applications. I don't know what you saw in this class. In a special session dedicated to mathematical optimization, there is not going to be only optimization. There are, I think, a couple of routine optimization group, but all the rest are going to be different and in way interesting ways and techniques and topics. The thing is that I believe this kind of session will take place in this exact room. I believe on Monday and Thursday. So if you're around, I think it's as I said, as a good place, right? As a good event for them. And for students, is like 150 reais. And if you're even members of the Mathematical Society in Brazil, or any other mathematical society of South America, or Latin, is even cheaper. So I think it's worthwhile. There are interesting plenaries, the keynotes and sessions and posters. So it's going to be fun. All right. So that concludes this talk. So let me stop. That concludes these lectures, actually. The series, this mini course, right? Where I hope that you learned something, or at least you were somehow interested, right, in learning more, or going even further into depth, right, on this topic. And yeah, if not, I wish you anyway a good rest of the summer, right? The summer break, and all the best with your future endeavors. Right? All right. Thank you for attending, and I'll see you.